Hello, ladies and gentlemen. Today we are talking concerning 6.3, section 6.3, talking about using similar polygons. So we've done a lot of review of ratios and proportions, and now we're really going to see where those come into play in geometry. This whole chapter is about similar figures. We'll talk a lot about triangles, but in general, say similar figures or similar polygons. And the everyday definition of similar figures or similar polygons is that you have two shapes that are the same shape but different sizes. You know, we're used to seeing similar figures everywhere. We see, if you're watching a movie, let's say on a television screen versus a movie theater, one movie is obviously larger than the other, different size, but everything is the same shape, nothing is distorted, so we consider them to be similar. The technical geometric definition that we'll use in this course is a little bit more detailed. We know that in similar polygons, the corresponding angles are all congruent. That allows it to maintain its shape. And the corresponding sides are proportional. That also allows it to maintain shape while being a different size. And so down here we have an example of two different similar shapes. These are quadrilaterals, that all the corresponding angles are congruent, such as these here. And we see all the corresponding sides are proportional, which we'll look at the numbers in just a minute. This should be somewhat familiar because we did work on an activity in class regarding similar shapes, and we should have discovered that the size proportional for ourselves. With these two shapes, if I were to list all the corresponding angles that are congruent, I know that J corresponds with C. Put J first. And it's easy to see these because these two shapes aren't rotated or flipped. They both have the same relative position. O and A are corresponding, so angle O and angle A. H and angle R, angle N, and angle L, the bottom right. So all of these are our corresponding angles. They're all congruent because these shapes are similar. When we're talking about the ratios of corresponding sides, if I pick one pair of corresponding sides, like JO and CA, I would say the ratio of JO to CA. If I were to pick a different pair of corresponding sides, like JN and CL. Since these sides are proportional, these ratios should be equal, as we saw in our activity. If I were to pick OH and AR, again, all of these ratios should reduce to the same value because they're all proportional. They've all been multiplied or divided by the same number so that they're changing the same amount. HN and RL. Again, these are all proportional. They are all equal to each other. And just like with congruent figures, with similar figures, we can write what is called the similarity statement. So we can say that our first quadrilateral, I'll call it JOHN. So this is John. And instead of saying congruent with an equal sign and a tilde, similar is just a tilde. So let's write it like this. John is similar to Carl. John and Carl are the same shape, but they're different sizes. So that's what we mean by a similarity statement, just like when we wrote a congruence statement back in chapter 4. Let's do some problems, though, involving similarity to get some a better idea of what it is we're talking about. So for this one, we know the triangle RST is similar to triangle XYZ. That's how we would read this. Triangle RST, similar to triangle XYZ. Well, first of all, we're going to list all the pairs of congruent angles. Well, again, these aren't rotated or flipped or anything, so it's easy to see that angle R and angle X are corresponding, and they're congruent. In this case, since it says congruent, I'm going to write angle R is congruent to angle X. Likewise, angle T and angle Z, and angle S and angle Y. So that's my list of my pairs of congruent angles. Then it says, check that the ratios of corresponding side lengths are equal. So we're going to check these ratios are all equal. Well, let's take one pair of sides ratio and see what that reduces to. So let's pick 25 and 15. They're corresponding. So I'm going to say 25 over 15. And that will end up reducing to 5 over 3. If I divide 25 and 15 both by a common factor of 5. For a second pair, let's pick 20 and 12. Now, since I started with the larger one, 25, over the smaller one, 15, I need to do the same thing here. Larger one, 20, over the smaller one, 12. Going from my larger figure to my smaller. I need to be consistent. And with 20 over 12, what common factor do I have? Well, they're both divisible by 4. And if I end up reducing that, I end up again with, the right color, 5 over 3. Okay, so 2 of them work so far. When I pick my last pair of sides, it should also reduce to 5 over 3, so 30 over 18. You can divide both of these numbers by a common factor of 6 and end up with 5 over 3. So yes, I end up with 5 over 3 for all of these. So yes, my sides are all proportional because those ratios are all equal to each other. And finally, for part C, write the ratios of the corresponding side lengths in a statement of proportionality. We've actually already written one of those before. If I were to write side RT, where T is at the top here, and compare that to XZ, that should be equal to RS over XY, another pair of corresponding sides, RS and XY, which should also be equal to TS to ZY. So we're writing a statement of proportionality. We're just writing our proportions without the numbers. We're writing them just with the labels. So RS instead of 20, XZ instead of 15, etc. Let's keep going. Now we're going to determine if these polygons are similar. If they are, we're going to write a similarity statement and find what's called the scale factor, which we'll talk about in just a moment. So, our two requirements for similarity are, 1, our angles should be congruent. Secondly, our sides should be proportional. So let's check and see if these are true. Starting with the angles, we do have 4 pairs of congruent angles. 3 tick marks and 3 tick marks, 2 and 2, 1 and 1, and then right angles. So yes, all of our corresponding angles are congruent, so that works. Let's check and see if our sides are proportional. 20 over 25 should equal 16 over 20, which should equal 12 over 15, which should equal 24 over 30. So all these ratios should end up equaling each other. Now as a reminder, this time I'm starting with the small side over the large side, so I need to be consistent. Small over large, small over large, small over large, small over large. Consistency. So let's reduce these. 20 and 25 have a common factor of 5, and if I divide both by 5, I end up with 4/5. Here I have a common factor of 3. 12 divided by 3 is 4. 15 divided by 3 is 5. So again, 4/5. 16 and 20, if I divide by 4, 4/5. And 24 over 30, if I divide by 6, 4/5. So in this case, the sides are proportional, so yes, these two shapes are going to be similar. For a similarity statement, I can just name one of them, so I'll call, let's see. Well, I'm talking about ZYXW and FGHJ, so let's do this in the correct order. ZYXW first, so I'm just going to name that ZYXW is similar to. Let's make sure I put the points in the right order. ZYXW, so it should be FGHJ. Now, I'm going to find the scale factor of ZYXW to FGHJ. So that's comparing my larger one to my smaller one. Well, your scale factor is this number that we reduced, which in this case is 4 over 5. However, 4 over 5 is comparing the smaller one to the larger one, where this says find the scale factor of the larger one to the smaller one. So instead of 4 over 5, I'm going to write 5 over 4, or I can write it this way, either way is fine. And I just label this scale factor as SF. So there's my scale factor. It's that common ratio that these reduce to. That common scale factor, in this case of 5 over 4, is kind of like reading a map. For every 5 units over here, it equates to 4 units over here. Just like on a map, maybe every inch represents 50 miles. That's an example of a scale factor in real life. This scale factor is purely geometric in the context. There's no life application, there's no inches or feet or anything, it's just two numbers. Every 5 units over here represents 4 over here. That's the ratio that compares these two figures. Let's continue on. Let's use scale factor and similarity to solve for missing sides. So for this problem, we're given the fact these two shapes, triangle DEF and triangle MNP, are similar. We're going to find the value of x. Well, if these are similar, all of our sides are proportional. That means that 9 over 12 is equal to 12 over 16 is equal to x over 20. So all these should reduce to the same value, which is our scale factor. So if all these are equal, in order to solve for x, I can choose any two of these fractions and set up a proportion. So I can say that 12 over 16 equals x over 20. Cross multiply and solve for x. Or I could say 9 over 12 equals x over 20. As long as you write a proportion with one variable. So I could say 9 to 12 is the same as x to 20, or 12 to 16 is the same as x to 20. Either way is fine. Either way you do this, you will get the same answer. I'm going to choose the one with my smaller numbers simply because they're easier to work with. So if I cross multiply, I have 12x, and I have equals 180. And if I divide both sides by 12, x is 15. So since our sides are proportional, to solve for a missing side, you'll always set up a proportion, and you'll end up cross multiplying. Let's try another one. In this diagram, we are given the fact these two quadrilaterals are similar. Let's find the scale factor. Well, to find a scale factor, we know that all of the sides will reduce to the same fraction. That's our scale factor. So let's just pick one pair of sides and find the scale factor. So we're comparing QRST, which is our smaller figure, to ABCD, which is our larger one. So in QRST, let's say I'll choose 6, and that corresponds to 12. So 6 over 12. That reduces to 1/2, which is our scale factor. You can choose any pair of sides and reduce it to your scale factor. If I chose 8 over 16 instead, it gives me 1/2. If I choose 5 over 10, I end up with 1/2. So all of them will get me my scale factor. For part 2, find the value of x. Well, again, I'll write a proportion. I'll choose any pair of sides that I want to. In this case, I'm going to choose 5 over 10 because they're smaller. And that should be equal to comparing 4 to x. We can cross multiply and solve for x. You know that 5 over 10 reduces to 1/2, so you could end up writing it with your smaller numbers and reducing first. That's always permissible. So here, if I cross multiply, 5 times x is 5x, 4 times 10 is 40, divide both sides by 2, and x is 8. So I'm finished with part 2. If you did this with mental math, that's fine. Or if you actually ended up cross multiplying, that's fine too. You can say 5 is half of 10, so 4 is half of 8. Mental math, that's fine. And for part 3, find the perimeter of both figures. Well, we know that x is going to be 8, so if we find the perimeter of both of these, the perimeter of QRST, if we count all these up, is 23, and the perimeter of ABCD ends up being 46. Well, what do you notice if you write these as a fraction, as a ratio? Well, this reduces to 1/2. Yes, it does, because not only are our sides are proportional, but also the perimeters are proportional. The perimeters of similar shapes are proportional. That's true for any pair of similar shapes. Triangle, quadrilateral, anything. Perimeters of similar shapes are always proportional. That's a brief rundown of this section. There are a few other things we talked about in class. Not only are side lengths proportional, not only are perimeters proportional, but altitudes and medians and things like that are also proportional. But this should be enough to get you started if you were absent, and enough of a catch-up if you were in class or wanted a review. Any questions, as usual, feel free to email me, and I'll get back to you as soon as I can.